In this video, I will explain frequency response of an op-amp. Open loop frequency response. Open loop frequency response. That means without any feedback connection from output to infinity. Output to infinite. Open loop gain of an op-amp is represented by AOL without any feedback connection. Generally, op-amp symbol is like that: plus VCC minus VEE. These are the power supply pins. V0 is the output pin. V1 and V2 are the two input pins. And VID is the differential voltage. Generally, bandwidth of an op-amp is ideally infinity. Open loop gain of an op-amp is constant for all frequencies from 0Hz to infinity. 0Hz to infinity. That is, gain of an amplifier is constant from 0Hz to infinity frequency. Due to capacitive effects, the gain of an operational amplifier is decreases like that. Decreases at a frequency due to capacitive effects. Practical op-amp gain decreases at high frequencies due to some capacitive effects. Due to some capacitive effects. The reactance of that capacitance Xc is equal to 1 by 2 pi Fc. As F value is at low, Xc is very high. That means Xc acts as open circuit. F is very high. Xc having some finite value. That value is included. Due to that value, the gain of the amplifier, open loop gain of an operational amplifier decreases at high frequencies due to some capacitive effects. Capacitive effects of effects, physical characteristics of semiconductor devices. This is the one source of capacitive effect, that is physical characteristics of semiconductor devices. Op-amps are composed or constructed of BJTs and FETs with contains some junction capacitances. The first stage of an op-amp is a differential amplifier. Dual input balanced output differential amplifier. This differential amplifier contains either two transistors or two FETs having some junction capacitances. This is the first source. Second source of capacitive effect is the internal construction of an op-amp. Internal construction of an op-amp. In an op-amp, a number of transistors as well as resistors, sometimes a capacitors are integrated on the same material that is called as a substrate. In an op-amp is an integrated circuit. Integrate all the components on a single chip. That material is called as a substrate. In an op-amp, a number of transistors as well as resistors and sometimes a capacitors are integrated on a same material that is called as a substrate. The insulator. Substrate acts as an insulator and helps to separate these components. Here this is the capacitor is this one is a resistor and sometimes capacitors and sometimes the transistors. Sometimes FETs are integrated on the some material. That material is called as insulator. These materials are the subtractor acts as an insulator and helps to separate these components. Substrator. In an op-amp, a number of transistors as well as resistors and sometimes a capacitors are integrated on same material that is called as substrate. Acts as an insulator, helps to separate these components. The various components are connected by conducting paths. Conducting paths are which are used to connect the various components which are integrated on the op-amp integrated circuits. The various components are connected by conducting paths and the paths are separated by insulator. CP1 is the one conducting path, CP2 is the another conducting path. These two conducting paths are separated by insulator, produces a capacitor. Because of its construction, an op-amp may contain a number of such stray capacitances. The capacitive effects are two types due to physical characteristics of that semiconductor material. The first stage of an op-amp is a differential amplifier. The differential amplifier is composed of either transistors or FETs. These transistors and FETs exhibit some junction capacitances. The second source of capacitive effect due to construction of an op-amp. Construction means many components like transistors and resistors and also a capacitor which are integrated on the some material. That material is called as substrate. These materials are separated by or components are separated by an insulator. Sometimes these materials are connected by using some metal paths. These metal paths are separated by an insulator, exhibit some capacitive effects. The various components are connected by conducting paths and paths are separated by an insulator. This is also leads some capacitive effect. Because of its construction of an op-amp may contains a number of such stray capacitances. The cumulative effect of these capacitance due to the characteristics of semiconductor devices and the internal construction of an op-amp causes the gain to decrease as frequency increases. Due to these capacitive effects, the gain is decreases at high frequencies. For an op-amp with only one break frequency, we will represent all the capacitive effects by single capacitor. Suppose this one is the at low frequencies does not affect the gain, open loop gain of an amplifier. At high frequencies, the gain of an amplifier is decreases due to capacitive effects. Due to capacitive effects, this is called as one break frequency F naught. One capacitor is included. We consider one break frequency only. One capacitor means consider a single stage of an operational amplifier. That means we include a single capacitor effect. Sometimes operational amplifier is a high gain direct coupled multi-stage amplifier. That means multi-stages includes more number of capacitors are also included. More number of break frequencies are included. For an op-amp with only one break frequency, we will represent all the capacitor effects by single capacitor. Single capacitor. That means single stage. Single stage of an op-amp is single break frequencies. Equivalent circuit of high frequency model of an op-amp. This is the high frequency model of an op-amp. Here V1, the voltage applied at the non-inverting terminal of an op-amp. P2 is the voltage applied at the inverting terminal of an op-amp. This is Ri. VID is the differential voltage. VID is equal to V1 minus V2. Here AOL, open loop gain of an op-amp at 0 Hz frequency into VID. This is the voltage source, Thevenin's voltage source in series with resistance, some output resistance or not. Capacitive effect is also included in the circuit. This is the high frequency model of an op-amp. Modified model of an op-amp. Modified equivalent circuit of an op-amp. Because the capacitive effect is also included in that circuit, in that model. The capacitive effect is due to physical characteristics of that semiconductor material and also the construction of the op-amp. Op-amp with more than one break frequencies may represented by using many capacitors. By using many capacitors. More than one break frequency means more than one stage. AOL of F. AOL of F. AOL is the open loop gain of an op-amp at 0 Hz frequency. Consider this circuit. This circuit. Find out the AOL of F. Open loop gain of an op-amp with as a function of frequency. This is the AOL VID R0. C. Consider output section of that equivalent circuit of an op-amp. Capacitive reactance is equal to 1 by j omega c. R0 is the output resistance. That is nothing but Thevenin's resistance. AOL into VID. AOL is the open loop gain of an op-amp at 0 Hz into VID differential voltage applied at the two input terminals of an op-amp. This is nothing but Thevenin's voltage source. Apply voltage division rule. V0 is equal to total voltage applied to the circuit is AOL into VID into 1 by j omega c R0 plus 1 by j omega c. Omega is equal to 2 pi f. V0 is equal to omega is replaced by 2 pi f j 2 pi f c into AOL VID 1 plus j R0 2 pi f c by j 2 pi f c. Here omega is replaced by 2 pi f. Omega is replaced by 2 pi f. That is the reason here R0 2 pi f into jc plus 1. Next one, simplification V0 is equal to AOL VID, AOL into VID, j 2 pi fc, j 2 pi fc terms are cancelled. Therefore, finally AOL VID by 1 plus j R0 2 pi fc is there. Open loop gain of an amplifier as a function of f is equal to V0 by VID. V0 is the output voltage of an op-amp. VID is the differential voltage which is applied at the two input terminals of an operational amplifier, that is VID. This is the gain of open loop gain without any feedback. AOL open loop gain of an amplifier at a 0 Hz frequency by 1 plus j R0 2 pi fc. Let us define another term that is called as another frequency, break frequency. F0 is the break frequency. F0 is equal to 1 by 2 pi R0 into C. Therefore, 2 pi R0 C is equal to 1 by F0. R0 into 2 into pi into C is replaced by 1 by F0. Therefore, AOL of F is equal to AOL by 1 plus J F by F0. AOL of F is equal to AOL by 1 plus J F by F0. At 0, AOL is the open loop gain of an amplifier. Open loop gain of an op-amp as a function of frequency. This is AOL of F. F is the operating frequency. F0 is the break frequency of an op-amp. AOL is the open loop gain of an amplifier at 0 Hz frequency. Finally, AOL F is equal to AOL of F is equal to AOL by 1 plus j. 2 pi and 2 pi is multiplied here, numerator and denominator. 2 pi f, 2 pi f naught. Here AOL. AOL of omega. 2 pi f is omega. Here 2 pi f naught is omega naught. Omega naught plus j omega. Here denominator, in the numerator AOL 2 pi f naught. AOL 2 pi f naught is omega. Omega naught plus j omega naught. J omega is S. Therefore, open loop function of an op-amp in S domain is AOL of S is equal to omega into AOL by S plus omega naught. This is the S domain. AOL of F is equal to AOL by 1 plus J F by F naught. This is this complex quantity. AOL of F, open loop gain of an of amp as a function of frequency is a complex quantity. It has two functions, magnitude function and phase function. Magnitude function of a gain AOL of f is mod AOL of f is equal to mod AOL by square root of 1 square by 1 square plus f naught by f by f naught whole square. This is the magnitude function, and phase function is phi of f is equal to minus inverse f by f naught. Consider 741 C, IC 741C, the break frequency. Electrical characteristics of IC 741C op amp is break frequency is 5H, and open loop gain AOL is equal to H0H is 2 lakh. Therefore, magnitude function mod AOL of f in dB is equal to 20 log AOL by square root of 1 plus f by f naught whole square. 20 log AOL base 10 minus 20 log. Log A by B is base 10 is equal to log A base 10 minus log B base 10. Log A, 20 log A means AOL base 10 minus B is the square root of 1 plus f by f naught whole square. This is the AOL of f magnitude function in dB is equal to 20 log base 10, 20 log 2 lakh base 10 minus 20 log square root of 1 plus f by f naught whole square base 10. Find out values at different frequencies. 20 log 2 lakh 20 log 2 lakh base 10 minus 20 log base 10. Substitute f value. Square root of f value is 0. F naught value is 5H, because op amp from that data sheet f naught break frequency is 5H. 2 lakh is the open loop gain of an amplifier at 0H whole square. Therefore, 20, this value is calculate this value 106.02 minus 3.01, or this value is 106. This value is 106 dB. 106 dB. Next, coming to 5H frequency break frequency, that is equal to 20 log base 10, 2 lakh minus 20 log square root of 1 plus operating frequency f is 5, break power frequency is also 5, 5 whole square base 10, that is equal to 106.02. Here also 106.02 minus 20.04, that is equal to 86 dB. At a break frequency f naught, both the gain value decreases from 106 dB to 86 dB. Next one, at a 50H frequency, magnitude is equal to 106.02 minus 40, that is equal to 66. At 500H, at 500H, 106.02 minus 60 is approximately equal to 46 dB. At 5 kHz, Mod AOL of F is equal to 106.02 minus 80. That is at kilohertz. At 50 kilohertz, the value is 106.02 minus 86.02. That is 20. At 100, 50 plus 50, 50K plus 50K 100 kilohertz, the value is 106.02 minus 86 point. Here 86 in the above case, this is the 86. Here 86.02 is approximately equal to here at 50 kilohertz. At 50 kilohertz, 106.02 minus at 5 kilohertz, 60. This one is 500H. 5 kilohertz at the 500H. These values are again at 50H. At 5H, the value is at 5H, the value is 106.02 minus 3.01. That is 103. At 50H, substitute 50H here. The value is here 106.02 minus 20.04. That is equal to 86. At 500H, that value is 106.02 minus 02 minus 40. That is equal to 66H. At 5 kilohertz, 106.02 minus 60 is equal to 46 approximately. At 50 kilohertz, 106.02 minus 80 is approximately equal to 26. At 100 kilohertz frequency, operating frequency, 106.02 minus 86.02 is approximately equal to 20. At 1 megahertz, that is very, very important. At 1 megahertz frequency, 106.02 minus 106.02, that is equal to 0. Zero gain. Open loop gain in dB. One is very, very important. By using this one, by using these values, draw the open loop frequency response curve of an operational amplifier. This is the 0 dB. This one is mod AOLF in dB. Is on y-axis, frequency in H on x-axis, log scale. Here 20, 40, 20, 40, 60, 80, 100, 120, 120. That's one. At zero frequency, the value of gain is 106 dB. 106 dB. 106 dB. Consider this point here. 106. Next one, at a break frequency of an AOPAMP, that is 5H. After that only, this one is 10, 100, 1K, 10K, 100K, 1 mega. The gain at after a break frequency due to capacitive effects, the gain is decreases like that, and obtain 0 dB at 1 megahertz. At 1 megahertz, the gain is 0. This is the gain is constant. Open loop gain, that is a open loop gain of a function at 0H, that is constant up to 5H. After 5H, the gain is rolls off due to capacitive effects. Due to capacitive effects. Okay. Some points are discussed here, to be discussed here with the help of above graph. First one, the open loop gain AOL function f is almost constant, from 0h to from 0h to the break frequencies. From 0h to this break frequency 5h, the open loop gain AOL of f function is almost constant. At f is equal to f naught, that f is equal to f naught. This is the f naught. The gain is 3 dB down from its value at 0H. 3 dB frequency. At f is equal to f naught, the gain is down from the 3 dB value. From the value at 0H. That is 106. 106 minus that is 106 minus 106 dB minus 3 dB. That is 104 dB. This one is 104 dB. This one is 106 dB. Next, second point here is at f is equal to f naught break frequency or corner frequency. The gain is 3 dB down. The gain is 3 dB down from its value at 0H. From its value at 0H means 106 minus 3 dB. 3 in dB. This is the value of that gain, open loop gain of an op amp at a 0H frequency minus 3 dB. Minus 3. Hence the frequency f naught is called as hence the frequency f naught is called as minus 3 dB frequency. Minus 3 dB frequency. It is also known as it is also known as it is also known as corner frequency. Corner frequency. 106 minus 3, that is my 104. This is the at 5 kilohertz. The gain is a drop from value at 0 H. The gain at the value open loop gain of an amplifier at 0 H frequency. After F is equal to F naught. After F is equal to F naught means greater than 5H. Operating frequency is greater than 5H. The gain AOL of F mod AOL of F decreases at a rate of minus 20 dB per decade. The value is measured in terms of minus 20 dB per decade. Decade means a decade is a 10 times change in frequency. 10 times change in frequency. 5 into 10, 50. 50 into 10, like that. 50 into 10, 500 H. 500 into 10, 5K. Okay. Minus 20 dB per decade after break frequency. After F is equal to F naught, the gain AOL mod AOL of F decreases at a rate of 20 dB per decade, minus 20 dB per decade, or 6 dB per octave. A decade is a 10 times change in frequency, while octave is a 2 times change in frequency. As the gain decreases, slope of magnitude plot is minus 20 dB per decade. Second important point, third important point here is after F is equal to F naught break frequency, the gain mod AOL of F decreases at a rate of minus 20 dB per decade or 6 dB per octave. A decade is 10 times change in frequency, while octave is 2 times change in frequency. As gain decreases, a slope of magnitude plot is minus 20 dB per decade. Here one capacitor is included in our high frequency model of an operational amplifier. Only one break frequency is included. That is, consider single stage of an operational amplifier. Single stage, that means differential amplifier. First stage of an operational amplifier is the differential operational amplifier. Next one, consider in dB or in normal values. In normal values like that, this one is frequency AOL of F, not in dB. This is 0, 1, 10, 100, 10 cube. This one is 10 square. 10 square, 10 cube, 10 power 4, 10 power 5, and 10 power 6. This one is the corner frequency again. 2 into 2 lakh AOL. AOL is equal to 2 lakh at 0H frequency up to, that means 2 into 10 power 5. 2 into 10 power 5 at 0H frequency. The gain is constant up to F naught. Up to F naught. After that, the gain the gain of an operational amplifier decreases and reach to 1 dB. One value gain, open loop gain is 1 at a frequency of frequencies 1 megahertz. 1 megahertz. This one is 5H, 10, 100, 1K, 10K, 100K, 1 mega, 1 mega. Here not in dB values. Here directly mod AOL, mod AO, not mod. Here we use direct expression. Magnitude expression, not in dB. Not in dB. Mod AOL of F is equal to AOL at 0H frequency by square root of 1 plus F by F naught whole square. At F is equal to 0, AOL of 0H is 2 into 10 power 5, 2 lakh gain by square root of 1. F is 0H. F naught is also, F naught is 0H by F naught whole square. That is 2 into 10 power 5. At 0H, 2 into 10 power 5. At F is equal to 5H. Here at F is equal to 5H. F naught is also 5H. 5 by 5, 1. 2 into 10 power 5 by 2 into 10 power 5 by square root of 2. Like that, in that fashion, you have to calculate all the values of that mod AOL of F and draw this frequency response by using dB. Here dB normal values. Here we use normal values. This is the next one. At a frequency, the gain reduces to 0 dB. This is the, consider this is the frequency. The gain reduces 0 dB. This means 20 log mod AOF of 10 is equal to 0 dB, or mod AOL of F is equal to 1, or mod AOL of F 1 is equal to F is equal to 1. At a certain frequency, again reduces to 0 dB, reduces to 0 dB. That means 20 log based on mod AOL of F reduces to 0. 0 by 20, 0 by 20, 0. Therefore, mod AOL of F is equal to 10 power 0. That is equal to 1. Reach it to 1 or 0 dB. Or 0 dB. Such a frequency is called as gain over frequency. Such a frequency is called as gain over frequency. Either 1 or 0. That open loop gain of an operational amplifier reaches to either 0 dB or 1 at a particular frequency. That frequency is called as gain over frequency. That is 1. Such a frequency, such a frequency, such a frequency is called gain cross over frequency, gain crossover frequency, or unity gain bandwidth product. Unity gain bandwidth product. Bandwidth product. That is represented by UGB. Find out that UGB value. AOL of F is equal to, we know that AOL by square root of, this is the magnitude function, square root of 1 by 1 plus AOL by square root of 1 plus F by F naught whole square. At F is equal to unity gain bandwidth product, or gain crossover frequency, or gain cross over frequency. Mod AOL of F is equal to 1, or mod AOL of F in dB is equal to 0. Here magnitude function will not in dB. Therefore, mod AOL of F is equal to unity AOL by square root of here F is unity operating frequency, is unity gain bandwidth product by F naught whole square. That is equal to square root of 1 plus unity gain bandwidth by F naught whole square is equal to AOL. Unity gain bandwidth by F naught value is far greater than 1. Therefore, 1 is neglected. Square root and square term is cancelled. Therefore, UGB by F naught is equal to AOL. Therefore, unity gain bandwidth product is equal to open loop gain of an operational amplifier at a 0 Hz frequency into F naught break frequency. F naught at break frequency. Suppose get F naught is equal to 5H. F naught is equal to 5H. 0 to 5H. AOL is equal to 2 into 10 power 5, 2 lakh. Find out the unity gain bandwidth product. 2 AOL into F naught, 2 into 10 power 5 into 5H. 5 into 2, 10. 10 into 10 power 5, that is equal to 1 megahertz. Unity gain bandwidth product is 1 megahertz. At corner frequency F naught is 5H. Suppose AOL is gradually decreases from 2 lakh to 2 lakh to 1 2 lakh to 1. Find out this unity gain bandwidth product. Suppose at F naught is equal to 1 megahertz. At F naught is equal to 1 megahertz. Mod AOL of F is equal to 1. Find out unity gain bandwidth product. UGB is equal to AOL into F naught. That is equal to AOL is 1, F naught is 1 megahertz. That is equal to 10 power 6 H. This one is 1 megahertz. At gain also unity at a gain 2 lakh, unity gain bandwidth is 10 power 6 H or 1 megahertz. Even gain is decreases from 2 lakh to 1 1. The unity gain bandwidth product is 1 megahertz. In both the cases, this is the special feature of the operational amplifier. The gain bandwidth product is constant. The gain bandwidth product is constant. Unity gain bandwidth product is constant. Suppose 3 stages are used here. Stage 1. This is the stage 1. Stage 2 and stage 3. Corner frequencies are here, F1, F2 and F3. The transfer function of open loop gain of operation amplifier as a function of frequency is equal to AOL at F is equal to 0H pi 1 plus J F by F1 first corner frequency. Here we use 3 capacitive, 3 stages, each stage adding some capacitances C1, C2, C3. Due to these capacitances, F1 and F2, F3 corner frequencies are obtained. 1 plus J into F by F1, 1 plus J into F by F2, and 1 plus J F by F3. Therefore, here 0 less than or equal to F1 less than or equal to F2 less than or equal to F3. That the function is like that here. Mod AOL F in dB. We use in dB or in ordinary values. This one is F. At first corner frequency F1, the gain is decreases like that, minus 20 dB per decade. At second corner frequency F2, due to 3 stages, minus 20 minus 40 dB per decade, gain is decreases like that, open loop gain. This one is 0 dB. This one is 106 dB. And crosses 0 dB here at the third corner frequency F3. This one is unity gain bandwidth product. The frequency at operating frequency F is equal to unity gain bandwidth product or gain crossover frequency. At that frequency, the open loop gain of an operational amplifier is 0 dB or 1. This is the consider the stages of operational amplifier. We use some compensation techniques. Instead of 3, this one is minus 60 dB per decade. Instead of minus 20, minus 40, minus 60 dB, by using a compensation technique, modify this function, open loop AOL of F function. Instead of these 3 decades, we use only 1 decade, that is minus 20 dB per decade. Up to this one here. This is the compensation technique. Compensation technique is used to, instead of 3 reduces of that gain, only 1 reduce of that gain is considered, minus 20 dB per decade. In the next video, I will explain compensation techniques of that operational amplifier. Thank you.